So, hello, welcome everyone to my talk about extracting realistic pedestrian, cycling, and driving street networks from OpenStreetMap. So, the idea is to create this workflow to extract the different kinds of networks. So, first, a little bit of the structure of the presentation. Sorry. I will speak about why is this important, why we did this. Also, I will contextualize a little bit on the street network modeling, so how we model the street networks computationally. Then I will talk about the actual methodology that we follow, the workflow, how we process the driving network, the cycling network, the pedestrian networks. And then we also have something called assessment. So basically, you will see later how we are working on the assessment of pedestrian networks. And then some results to show how the methodology works, and some of the results, some of the simplifications that we did, and so on and so forth. And finally, some limitations because we're working with open data, with crowdsourced data. So, of course, there are going to be limitations. So let's start with the bigger picture. So we did this because we are working on something called the calculation of mobility indexes for active mobility. And active mobility basically means walking and cycling. So if you want to calculate such indexes, you need to isolate the pedestrian and the cycling networks. And this is something not done a lot in literature because they usually use the driving or the main street network. So it's important to differentiate to have accurate results and to have good results on these specific mobility indexes. So a little bit of a scenario that may have happened or not yesterday. Um, 35 degrees, 5 p.m. We want to go from point A to point B. This is Monster. So you plug in your favorite walking application or whatever application you have for routing, and this is the path it gives you. And when you get to point B, you are already melted and probably when degree one burns. But the actual realistic or the one path that you want to actually take probably is the second path that goes through the park because this is the actual pedestrian network. The other one is the driving network. So when you are calculating, when you are doing such kind of processing or analysis, and you're using the driving network, you get to incorrect results or non-accurate results. So this is important, and these realistic, accurate, and complete maps are important for many applications, such as routing, autonomous navigation, disaster response, and also for research, for these things, for calculating indices and calculating different things from the network. Okay. So a little bit of context again. We want to work with OpenStreetMap as our data source of information. OpenStreetMap is a global. I think all of us know what OpenStreetMap is. Crowdsourced database containing information mainly about the street network, points of interest, boundaries, and so on and so forth. Over 150 gigabytes of data as of last month, maybe more right now. And the data is enriched by tags. So basically, you can use key and value to filter or to process the information from OpenStreetMaps. And as a crowdsourced data set, it's also contain inconsistencies. Okay, so for example, we have different tagging conventions. So for example, for one city, you have one way to map the street network, the pedestrian network. For some city, a different way. You have mapping quality. Some cities have very, very, very precise networks. We are going to see a couple of those. We have also outdated information. Maybe the street doesn't exist anymore or never existed. But also we have contradictory information. So we have, for example, one say that this way is going south, the others other information says going north. So we have a lot of information and a lot of inconsistencies from crowdsourced databases. So then how to extract this realistic, how to extract the realistic data, how to extract the best data that we can get. First, we have our open data set, OpenStreetMaps, but then we have a set of filters and a set of post-processing algorithms to get this information, this raw information, and create and let's say overcome some of the inconsistencies that we have already found. So we have here, anyone wants to guess what city is this? Monster, exactly. We are around here, as you know. So the street network is actually the way or the system that models the roads or the connections in an area. And the street network can refer to the driving, the pedestrian, the cycling, and even the public transport networks. And we model this in a computational way using something called graphs. That is a data structure that is composed of nodes and edges. And for this research, we use something called a primal graph. So the more intuitive way of creating a graph where in the intersections are the nodes. So basically the points that you see here, this is not actually not Mustard, this is Athens. So the points that you see here are the intersections, the nodes of the graph, and the lines would be the edges. So with this information, with this data structure, we can create and we can process in a computational way such a street network. And then also to finish the contextualization, some applications that we can implement these two, maybe digital twin, urban digital twins. Digital twins need very accurate information, so this can be used for that. We have also developing cities. We are working with global, open source, crowdsourced data. So for developing cities, for the cities that maybe don't have the money or the budget to create authoritative data sets, this can be used for, let's say, as a baseline for that. And also for urban planners, analysts, and so on and so forth. So let's go to the methodology. I think I have already spent a lot of time on the context. So basically what we did was to create a methodology, a workflow for extracting pedestrian, cycling, and or driving street networks. Basically, we use the OSMNX as our baseline for downloading. Maybe you know OSMNX. It's a Python library for downloading OSM data, but we apply a set of custom filters other than the filter that they already have. And with the raw data that we obtain with the filters, we apply certain post-processing algorithms to remove the inconsistencies that we identify. And as a bonus, for the pedestrian network, instead of removing, we can mark the specific inconsistencies and we can assess the data for OpenStreetMap. I will go very fast through the workflow. First, we have that three different kinds of network: driving, cycling, and pedestrian. We have our area of interest. So with our area of interest and one of the specified street network that we want to download, we download a raw graph. With the raw graph, we apply some post-processing steps, and then we obtain the realistic street networks. We can also export them as GraphML for analysis on any kind of software, for example, NetworkX in Python, or as shapefile or GeoJSON for GIS software, such as QGIS or GIS. I didn't say ArcGIS, only QGIS. Well, to guide you through the workflow, I will use the city of Ottawa in Canada as an example. Anyone from Canada? Woo, no. So why Ottawa? During our, let's say, research or our exploration of data, we saw that Ottawa has had a very high mapping detail. Basically, all of the streets in Ottawa had separately mapped sidewalks, but then this led to inconsistencies because they were all separately mapped. Not all of them specified that they were separately mapped. So it led to duplication of the street network, basically. We'll see in a while when I talk about the pedestrian network. And you can actually see here um, the green ones are the pedestrian, the black ones are the driving network. So there is a lot of duplication if you don't apply the specific filters and the specific post-processing algorithms. So let's start with the easy way of the easy street network, that is the driving. OSM is historically car-centric, so there is not much to do with that. You just download the driving network, you filter out the pedestrian, the cycling network, and basically you create or specify that the network is a directed graph because the direction of the cars are important, and eliminate some disconnections between the graph to have like something very connected. Um, One other processing that we did was to eliminate something called interstitial nodes that basically allow us to um, simplify a little bit the network because street networks are very big. They can contain hundreds of thousands of edges and nodes. So doing these kind of processes, for example, here we have three nodes, two edges. If we remove this node over here, we will have two nodes, one edge, and basically the information is the same. So we basically simplify the network without damaging the information. And this is the result for Ottawa. You can see very clean and very nice street network for the driving. Then we get into uncharted territory. We have cycling networks. Cycling networks add an additional degree of freedom because cycling can happen both on the street, like on the normal street, if you share the street with cars, but they also have their own specific paths. So we have to account for those things. Um, but also because they share most of the traffic network, the direction is important. So we have to also represent them as directed graphs. From the filtering side, we basically did something similar to the driving network. We remove the forbidden access of the streets. We kept the segments that have the driving segments that are cyclable. So basically, the street network that can be shared with cyclers. But also we remove the pedestrians because if this not in every pedestrian path the cycle can circulate. This is a little bit complicated, but this is what we found also on the wiki of OpenStreetMap and on some of the guidelines of most of the countries. And then for the post processing, we didn't do much because the filtering already did most of the heavy work with the cycling network. We can see here a small example with the cycling network. Here we see that it removes this part over here that is shared, that could be shared, but it's actually a highway that is specified that is not cyclable. So we remove it because it's dangerous and it says that it cannot be used. And you see that although Ottawa has a lot of pedestrian that you saw before, it is not included here because it will not like share the pedestrian and the cycling paths of the city. Now let's go to the hardcore mode, that is the pedestrian network. The pedestrian network offers a lot of flexibility, so you can basically walk everywhere. And when we were on the, let's say, on the exploration phase, we saw that for very detailed cities or for high income cities, we have this information about the sidewalks and we have a lot of rules for not walking on certain streets or certain that can be walked. But on developing countries, But on developing countries, we have information. So there are roads that maybe they are not walkable for high-income countries, but in reality they can walk on there. So they have highways, very high highways that in reality should not be walkable. But you see then the mapillary, for example, imagery, and you see people walking on them. So realistically, you can walk on them. So for the pedestrian, what we did was to assume that the driving and the cycling networks are walkable unless specified otherwise. And we saw that this led to a very big data set. And from the perspective of the filtering, we remove forbidden access, indoor segments, because we are only interested on the external part, the outdoor. And then we remove this specific, that was my headache for a couple of months, the streets with explicitly separated sidewalks. But there is an issue. You have to specify when the separated sidewalk exists. But most of the streets do not specify it. So please, if you work on OpenStreetMap, specify when you create the sidewalks. So from the post processing, we did a specific algorithm for removing this that I will show you in the following. If you don't know, if you have a pedestrian paths, you can specify them in two ways in OpenStreetMaps. You can basically just put the street and say, okay, people can walk here because realistically, people can walk on the street. And usually, when you have the street, it assumes that it has sidewalks. But you have the second way, that is to create the separated sidewalks. So basically, you can see here the small dotted red lines. Those are the sidewalks. But when you have this configuration, if you don't specify that this street has a sidewalk, you are basically duplicating information for the engine of the routing engine or for the information that you are wanting to convey. So if you download this street network for pedestrians, you will have the street and the sidewalk. And this will lead to even bigger graphs that they already are. So if you don't specify, inconsistency arises. This is, for example, the example of Ottawa of all the specific paths that were not including the information about the separation. So it's a lot, even for a developing country, for a developed country. So how we remove this inconsistency? We did something, let's say, more on the geometrical part. We created a buffer on each of the specific on a specific street segment, and we identified all of the sidewalks that are close, and if they match the size and the angle, the street segment is removed. This is very complex because when you have graphs with a lot of edges, a lot of nodes, you have to work with the smaller parts. So basically, we speed up this computation by using an spatial index. So basically, we took this buffer, we only take the specific sidewalks that are close to it. We identify the intersection, the angle, and the length. And if it matches the specific road, we remove the road. And the result is something like this. If you see, all of the yellowish streets are the driving streets, and they have like a border. And this border are the two sidewalks. that are separated. Okay, so it works for most of the streets, and you will see how it there in the results how many streets got deleted from the methodology. Okay, and then just for a bonus, if you instead of deleting the street, you mark them, you have an assessment. So with assessment, you can, for example, identify which streets have certain inconsistencies, and then you can fix them using the editor, or you can use, for example, a specific editor or game that we have now for OpenStreetMaps to identify and to correct such issues, such as the street networks. We have this example of Uganda and this example of Sarajevo that also on the even it's a okay. So we have African country, low income economy, um, European economy, middle income, European country, middle income economy. And we have the same issues. So it's not something that only happens in third world countries. It's also something that is happening everywhere, even in Europe and US and in Canada. So as for the results, we downloaded the street network for 5 cities all over the world. We have, for example, Amsterdam. We have Addis Ababa in Ethiopia, Montevideo, Kampala, and Ottawa. And we saw, for example, for Ottawa, as I was telling before, a reduce of 15% of the edges of the graph with our with the processing algorithm that I showed you recently. And surprisingly, for Amsterdam, we had an increase in the information. Why? In Amsterdam, we had an increase because we were not the base OSMNX algorithms are not considering the pedestrian paths that can be shared with the cycling as paths that can be walked. So all the additions were by cycling paths that can be shared with pedestrians, and in Ottawa, the reduction was by more than 20,000 edges, and it's basically the removal of all these specific small segments of the driving street that has already the sidewalks attached to them. And then we have also limitations on this methodology because we are working with crowdsourced data and it's very complicated. So we have an issue that actually, if you have false matches, so for example, this is not actually a pedestrian street, but it's considered, it's tagged as pedestrian street, if I'm not wrong, like the tag is pedestrian street, but it's actually a normal street. So these false matches disconnected the graph. If you see here, if you remove all these red lines, this part gets disconnected from the other side. So you have to walk all this way around this street to get to the other side. And this is something that we don't want. So this is not free of limitation and not free of errors as any algorithm in the world. But as we are already in like in the third iteration of this kind of process, so we fix most of the issues. Just to conclude, well, we propose this general and global methodology for extracting realistic pedestrian, cycling, and driving networks based on open data, filters, and post-processing algorithms. And we can also benefit from the assessment of this of OpenStreetMap pedestrian networks using these algorithms. We tested the methodology on 5 cities, but from the project that I was talking in the beginning, we are actually doing the analysis of the street networks for more than 180 countries, also all the capitals of the world. So that was the idea of having this general and global methodology to be able to download any kind of country or city in the world. As you can see, reductions were seen on most of the pedestrian graphs because of the limitations and of the inconsistencies that I already talked. And then just for the limitations and for the future work, the usage of global data and crowdsourced data, of course, includes certain inconsistencies and certain errors to the algorithms and to the methodology. And also the complexity of the street networks is a limitation because everything is too difficult sometimes to process, especially with very big cities. So for this, we actually implemented multiple, for example, the spatial index was used to speed up the computations of the comparisons, but we also have some parallelism in this. So for example, instead of processing one by one, we process by batches, so it's very fast in the end. In the end, for the 180 cities, we took around 3 days to process all of them with some indexes related to proximity. So we had also like shortest pass and everything. It's a very interesting work. And one of the future work also is related to public transport. So we also want to include public transport in this information. The repository, you can access it here. It's still a little bit work in progress. we want to create this as a service. So basically, that you say, okay, I want to download for this specific city. It will take care of the geometry and so on, and it will download the street network. And you can find me also on GitHub over here. Thank you for your attention.